Let's take a look at some graphs. So if we know position, velocity, acceleration, what do we expect to see in graphing those? So first, in a position versus time graph, if you recall, average velocity equals change in position over change in time. And we know that this is the slope on a graph of position versus time. So if I graph position versus time here, so I've got time on the x-axis, and so we'll say that's time in seconds, and I've got position on the y-axis, and we'll say that's that should be in meters. And actually, instead of graphing like this, I want to do a slight change so that we can have a couple things in here. Okay, so again, position, time. So this right here is going to be 0 meters. That means whatever you're measuring with respect to, this is the origin. So that might be the starting point of a race. It might be the ground level. It might be the middle of the classroom. Whatever you want it to be, it's 0. That means you can have positive and negative. Positive just means to one side, negative means to the other. So now let's come back and let's imagine we throw some information here. So a real basic shape just like this. So what do we see here? Well, first, this first part, we see that the object is staying in the same position over time. In other words, it's not moving. Then we see the object changing its position over time. In other words, we see some movement, some velocity. And in this case, because it's a nice straight line, we can just take the slope of that to find the velocity here. This is technically an average velocity if I calculate using the endpoints, but because the slope is the same everywhere, that's also the actual velocity. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's negative 9 meters. So let's just say each of these boxes is a meter. And then it's 1, 2, 3, 4, 5 seconds. So negative 9 over 5 seconds, which means that has a velocity of negative 9/5 meters per second equals the velocity for this region here. We see that also works for this region because there's no change, so it's 0 meters divided by however long, so it's 0 velocity. So when you look at a position versus time graph, you can find the position by just looking at the graph and finding where an object is. You can also find the average velocity or the velocity by looking at the slopes. On a velocity versus time graph, we can rearrange that average velocity, which remember is delta x over delta t. We can rearrange that to be delta x equals v bar times delta t. And if this v bar, we can I'm going to be a little hand wavy here. There is a more rigorous mathematical explanation and proof. If you want to learn about it, let me know. But otherwise, I'm just going to kind of say, if we look, this is on a velocity versus time graph. This is kind of like multiplying an up by a side. So if I have this, this is represented by the area under the curve. So from this time to this time, if I calculate that area, that will tell me how far the object has moved in this time interval. So in this case, it's 1, 2, 3, 4 meters per second times 1, 2, 3, 4, 5, 6, 7 seconds, and that gives me 28 meters per second. Now we need to be a little careful if we're going to do this for the whole graph, because on these sides, because these triangles, we need to calculate the area of a triangle. So 1, 2, 3, 4 by 1, 2, 3, 4, 5. It would be 5 times 4 divided by 2. So this would mean delta x is equal to 20 meters. And then over here we have delta x is equal to 16 meters, because it looks like it's more like 4 by 4. Did I just do that wrong? No. Divide by 2, because it's a triangle, 10 meters and 8 meters respectively. So the total represented by this is 28 plus 10 plus 8, so 46. This also means you can have such things as negative areas, which just mean a negative change in position. It went the opposite direction. So we also have a velocity versus time graph. We also have acceleration. And if you remember, average acceleration is equal to change in velocity over change in time. So this, like before, is represented by the slope. So if I have that velocity versus time graph, and have something like, say, that. Then in this region right here, we go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. So this is 6 meters per second divided by 8 seconds, which will give me 6/8, 3/4 meters per second times 1 over seconds, because it's in the denominator. And that gives me 3/4 meters per second squared is my average acceleration, which, because again it's a constant, is also the acceleration that whole region. So again, the main thing I want to point out is just looking at this as the slope. Lastly, we're going to look at acceleration versus time graphs. And remember, change in velocity, we're going to do the same thing we did with the velocity versus time graph for position. I'm going to rearrange this and get that the change in velocity is the average acceleration times change in time. Average acceleration times change in time. And this is represented by an area. And again, that area can be positive or negative. So this is an acceleration versus time graph. And I have something like this. Then this area right here is 2 by 4, so that will be plus 8 meters per second is my change in velocity. Here, that's going to be minus 6 meters per second is my change in velocity. So really, I just want you to be thinking, if you're kind of trying to summarize all this together, position versus time graph, the slope is the velocity, and know why. Velocity versus time graph, the area is the change in position. The slope is the acceleration. And then the acceleration versus time graph, the area is the change in velocity. This is something that is a huge help for you later on, but it also takes some time to get used to and comfortable with. So don't stress if you're still kind of sorting things together. Let me know what questions you have, and feel free to check in on that.